Alright, so let's continue. We talked about race conditions, which means things are happening out of order or causing issues with the data we have because they're sharing. So we come up with this idea of critical sections, parts of code where only one program can be in there doing anything at one time. Right. And then if we think of critical section as a part where we must have mutual exclusion, progress, and bounded weighting, then we can come up with some schemes. But of course, there have been many people who have come up with different schemes in the past, and we're going to discuss a few of them. We're going to start with Peterson's solution. Right. So the idea that Peterson had was to say, well, we need to be able to have something to record our interest in entering a critical section, right? And we also need to be able to tell whose turn it is. Right. So if two things are competing, right? So let's say, um, sorry, process I and process J. Both of them are competing to enter some secret room. There are two things we could do. First off, we could have a variable called turn, and whenever it's someone's turn, for example, if it's the turn of I, we'll set it to I so that um, the process called I can tell it's his turn to go in there. And then, of course, we could also have these flags, right? So flag of I and flag of J to indicate when someone wants to enter, right? Right, so Peterson's idea, again, in simple form. So for example, if there's process 1, process 2, process 3, and so on, up to maybe process n, that means we are going to have many variables, flag of 1, flag of 2, and so on. Which when the process is not interested, will set it to false. But anytime a process wants to use a critical section, for example, if process 2 wants to use a critical section, it will set it equal to true that it's currently interested in entering the critical section. Right. So you can think of processes as all these secretaries who are taking calls, right? But before they actually access the shared notebook, they will maybe raise a hand to indicate they are interested. So in real life, we do see Peterson's solution at work. So in a classroom, maybe people want to ask a question, but everyone raises their hand to indicate, well, the ones who want to ask questions would raise their hand to indicate whether or not they are interested in currently speaking. So, I mean, the act of speaking is the critical section, right? In Peterson, that was one of them. And of course, we have the turn variable. Right? The turn variable, meaning we need to have some variable. Maybe when we set it equal to 2, then we know that it is a turn of 2 to talk. Or we set it equal to 3, it means it's a turn of 3 to talk. We set it equal to 8, it means it's a turn of 8 to talk. Now, if we combine these two things, the ability to indicate, maybe by raising hands or by shouting, um, and we also have this turn variable. The combination will allow us to have a critical section. So in a classroom, for example, students raise their hand and a teacher picks. So let's say um, person number 2 raises their hand, person number 3 raises their hand, indicating they want to do a critical section. And the teacher says, well, it's 3. That means that currently the person who is 3 can then go off, finish talking, right? But the interesting thing about Peterson's solution is, as far as the code is concerned, what tends to happen is after someone finishes accessing the critical section, they often will pick someone else to go in after them, right? So the idea being, if we have a process who is process M, so M is some integer, so maybe for you M is 1, another person M is 2, and so on. What they'll do is they'll set M equals to true. That means that's what their code will do, indicate that they are interested. And they're going to say, while there is someone else, or it is not my turn, I'm going to wait. Right? And in code form, this is usually written as while some condition. Right? This will actually create, so long as maybe condition was true, this would create an infinite loop. So this would be a loop. This is actually called busy waiting. So it means you check on a condition and you keep checking it. So you waste all your cycles checking it, and hopefully some other process changes the variable value and you go. So I'm writing this in plain English. That means while there's someone else, right, who gets to go first, or it is not your turn, you have to wait. Right. And the important part is once you know that there's no one else who is waiting or it is your turn, you can go in. Right. This should be end. So one of those. Right. While there's someone else and it is not your turn. But the moment it's your turn, you get to go. And if there's nobody, so consider if you raised your hand and you're the only person in the classroom with a hand up, right, you could just assume it was your turn, you could speak. But if you raise your hand and there are other people whose hands are up, that means you have to wait for the teacher to pick a turn, whose turn it is, right? So that's basically Peterson's solution. And in Peterson's solution in code, you go to your critical section, and after you go to your critical section, there are usually two things that happen. For most people, what they'll do is they will select someone else to go by setting the turn variable, right? So maybe if, in this case, process number 3 finishes, knowing that it's finished, it would set it's no more interested, and then it can take the turn and say, person number 2, please go ahead. So you don't always need a third process to come in to set the turn variable. It could just be a convention that maybe, so consider this. Let's say there's a class and there are many students in the class. They will raise up their hands. The teacher will pick the first person to speak. But after the first person speaks, that person can pick someone else who has the hand up. Right. And so that is Peterson's solution. Right. I'm just going to show briefly the code from the textbook. This is code from Silvershad. It's a bit scary, but I don't think it is that scary. Right. Let me make this Korea and smaller font. All right, so let's look at this code, right? Now the code says people want to enter. Waiting is like the interested variable. If you say, okay, waiting, if it's process I, so we're assuming that the process I, which is some integer. So if it's process 1, I will be 1. If it's process 2, I will be 2, and so on. Process I is interested, right? And that usually begins by setting some value in an array to true. Initially, everything is false, meaning you're not interested. But if you're interested, you set it to true, right? And you're going to be waiting if it's not your turn and if the place is locked. So there's going to be some variable that we are going to use for locking, right? We are going to be waiting. And if you get to go in, you can do some work. So this is the critical section, which could have some code. And then when you finish, this code is actually very interesting. It's from the text, but when some people see it, they get worried. Right. So I'll just explain what's going on. So it says, searching for someone who is waiting. Now, if you are in a loop, right, if you are person number I, what you need to do is you need to go to I plus 1, I plus 2, I plus 3. So what it starts to say is, if I'm, let's say, 10, n is the total number of processes. Let's say n is equal to 11. Right. So if I'm 10, 10 plus 1 modulo 11 would go to 0. Right. So in other words, you want to create a looping counter so that anytime, let's say, process number 1 finishes, it will check for 2. If 2 finishes, it will check for 3. So everybody who finishes checks to look ahead to see if other people are interested. Right. So it's saying, so while waiting of J, so what it's saying is, while there's nobody else, so it's going to be looping. This loop is interesting. So while there's nobody else, it's going to keep going until it finds somebody who is interested, right? Someone who's made the interest true. If somebody is interested, right? What the code did was to actually set the waiting. So remember, people were going to be waiting. So look at this condition here. Waiting while, so he's waiting while this is true, meaning he says he's interested, means he's interested, it's true, and he's using that to wait. So if someone else sets it to false, he would leave this loop, right? And that's what actually happens at the end here, right? Meaning if somebody comes in and sets it to false, that means that he can go in. The other condition is someone can say the lock is free. The lock is free when it's false. And that means if it's set to false, then someone else can go, and that is the looping condition here, right? But I think as far as Peterson's solution is concerned, the high level discussion, meaning there is some array or some variable for every single person who is waiting, and everyone who is waiting gets to indicate by setting their value equal to true. So if it's false, so initially when the program starts, everybody is false. If process number 3 is interested in entering a critical section, it sets it to true. So you can think of people in a class, someone raised their hand to indicate they're interested. And there's a variable, the 10 variable, that everyone looks at. So that's the teacher or whoever the presenter is, who's going to pick somebody and say, well, I think that 3 gets to go. And so what's happening is, after that first process, whoever finishes speaking, so if 3 has finished, 3, so what that code was doing is 3 will look at 4 and say, is 4 interested? Is 5 interested? Is 6 interested? Is the last person interested? Is n interested? If n is not interested, what about 1? What about 2? If nobody is interested, then of course you can let go and say, well, it's nobody's turn, right? So this is some value false. It's nobody's turn, right? But if someone else was interested, let's say 3 was the person who said he was interested, and somewhere along the line, P of 100, the flag is true. When 3 has finished, so if the teacher comes and says, okay, 3, you can go. When 3 finishes, 3 is going to keep searching. Search at 4, at P5, P6, all the way till P100. And says, well, I found somebody who gets to go, and by setting and telling everybody, hey, I'm the person who finished speaking, I'm saying 100 is next. That means that the next person is actually picked by the person who kindly just finished, right? So this is Peterson's solution, a bit modified, right? And you can see there are things here. So mutual exclusion is guaranteed because there are 2 things that people who are going to enter are checking. They're going to check if there's someone else who is interested and it is not their turn, right? So if it's your turn, you can go in, right? Now, in the textbook, what they tend to do is everybody, when they're entering, tries to set n equals to m, meaning everyone who's entering tries to say, hey, it's my turn. Meaning, if 6 or 7 people are all trying to compete, only one person would get to set the variable, and then that person gets to go, right? So if 10 is set, so that's 1, right? So there's mutual exclusion because everyone is checking to see, is it my turn, and who else has the hand up? There is progress because in any scenario, someone gets to enter the critical section. It's not going to be that there's nobody in the critical section. And bounded waiting, there's actually going to be bounded waiting because if there are, let's say n is equal to 1,000, right, and everyone else is going, everyone else is interested, and everyone was interested, right? What's going to happen is if the cycle loop is taken, so if P3 were interested and he finished, he would pick P4, and if P4 finished, he'll pick P5, and P5 will pick P6, and so on. You create this loop, and you realize that the most you can wait is for one sort of cycle to complete. So as if everyone was interested, as if all 1,000 were interested. After 1,000 turns, you would get to go, right? It's not that you'll be skipped because the idea is it's now in a circle. So 1 would look out for 2, 2 look out for 3, 3 look out for 4, 4 look out for 5. 1,000 would look out for 1. It's in a circle now. So everybody's going to pick someone else to go, right? So that means there's this priority, but the priority is in a circle, right? And so there's definitely going to be bounded waiting, right? In real life, you've seen bounded waiting maybe at the bank where everybody picks a ticket number, and you can tell how long you have to wait by looking at how many people are ahead of you. So you don't go to the bank and pick a ticket number and you never get to go because the way it's run, a little bit like Peterson's solution, everybody is actually looking at the person who is ahead of him to see has he finished. If he finishes, then he goes. And if there's nobody there, so maybe person ticket number 10 didn't show up, ticket number 11 will just go because he says, hey, there's nobody ahead of me. So Peterson's solution actually solves mutual exclusion, progress, and bounded waiting. And bounded waiting especially means you have to have a scheme to make sure everyone has a turn, or everyone waiting, right? So this is Peterson's solution.